Hi, so good evening everyone. So today we'll start with the problem solving session corresponding to week 4's content. So today we'll primarily delve into topics related to in more depth into controllability. Last time we saw most of normal controllability cases and how to find controllability and so on, and we delved a little into linear algebra topics like what is the image of a s- number of vectors of a matrix and so on. So today we'll look a little deeper into controllable or non-controllable, uncontrollable systems and further explore a topic of stabilizability. And in particular, we'll look at how to decompose any given LTI system into controllable and uncontrollable portions. Okay, so with that, we'll start with solving some questions. And as usual, if you have any doubts or anything, you can interrupt me at any point, and let's try to be as interactive as possible so as to learn the maximum from this. Okay, so here's the first question. We have a system x dot equal to ax plus bu. Now assume that ai's are all non-zero. Okay, these ai's are all non-zero. Then we have to choose the correct statement. So let us look at the options. If AI not equal to AJ and so on so on. System is controllable. So we basically want to find out some conditions, like this could be one of the condition, AI not equal to AJ for all I comma j and all BI not equal to 0. If BI not equal to 0, so we want to find out under what conditions this given system defined by this A matrix and this B matrix is controllable. So as discussed previously, what is necessary for controllability? Any one of you?
Sir,
Yes?
sir, rank of controllability matrix equal to the order of the parent matrix, like A.
Right. So here in this case, we want the rank of controllability matrix to be 3. So let us first start out by finding the controllability matrix. So
Yes,
we
sir.
know that controllability matrix is B, AB, A square B
A square B.
for a 3 cross 3 system, third order system. So let's find this out. Let's take 3-4 minutes to find this out. Then we'll start resume our discussion.
सर
Tell me.
सर ऑप्शन नंबर 1, क्योंकि सर असाइनमेंट में आया था तो मैंने सॉल्व किया है.
Oh, okay. So, but okay, let's do the procedure once again.
ओके
Uh,
सर.
okay, tell me what is the controllability matrix, and if the other participant has not tried this out, let's take few more minutes. Yeah, so we were discussing this question where given this system specified some A and B, we want to find out under what conditions is the system controllable. So let us start out by finding out the controllability matrix, and we'll resume the discussion in a couple of minutes. So I'll start out here. Tell me the other columns. When was the submission date for this assignment?
सर
When was the submission?
24.
24.
24
Okay.
है.
Yeah, thank you. Okay, so whenever ready, tell me what the controllability matrix is.
सर
Yeah.
सर मैंने इसे A1 A2 A3 की जगह पे कोई वैल्यू एज्यूम करके किया था, जैसे लाइक A1 इक्वल टू 1, A2 इक्वल टू A3 इक्वल टू 3, and B1 1, B2 1, 2, B3 like that.
Okay. So, but we are looking at a more general condition because let's say you take a particular value of a1, a2, a3 and b1, b2, b3, and then let's say that particular value satisfies one of this condition or one of this condition or one of this condition. Okay,
So
let's
first
take
one.
the case first that for any given set of a1, a2, a3, b1, b2, b3, let's say it does not satisfy this condition, this condition. So is can we generalize that this statement will hold true? I mean, this statement will hold untrue. That is, will it be false? So what I'm asking is, let's take a1, a2, a3 as 1, 2, 3, and b1, b2, b3 as let's say 0, 1, 2. Okay. Then clearly b1 not equal to 0 here. Sorry, b1 equal to 0 here. Right. So then if I see that system is not controllable, right? If I see that the system is not controllable, then does that mean that this statement is false for all such cases? Is my
Yes, sir.
question clear?
Yes.
So, so can I generalize from a particular set of values? Is what I'm asking.
Yes, sir.
Okay. No, like, okay. Let's take some more examples. Okay, let's take a case such that a1, a2, a3, a4, b is b1, b2. So I'll take a particular special case. Right. Is this system controllable? So what is the controllability matrix? It is B first, then AB. This system is not controllable, right?
Yes, sir.
So
Yes, sir.
so can I say that for all like if A1 equal to 1, let's say A3 equal to 0 and B1 equal to 1, system is not controllable. Can I make a statement like this?
No, sir.
No, right? So similarly, in this situation as well, you have to take a generalized version as given in the question and then try to find out the controllability matrix. And then if you get some condition like this or like this, then you can definitely say that some statement holds. But if you take a specific case and try to generalize, then that won't work, right? Is what I tried to explain here clear?
Yes, sir.
Okay, so let us now find out the controllability matrix for this given system in its general form with A's and B's. So the first column is just B, which is B1, B2, B3. What about A into B? What should it be?
Sir,
Yes,
A1 B1,
A1, B1,
B2 B2,
A2, B2,
A3 B3.
A3, B3. Now what is
So
A
next
square
one.
B?
So A1 square B,
A1 squared B.
A2 square B2,
Yeah,
A3 square B3.
yeah. So this is the controllability matrix, right? So now tell me what is its determinant? This is the matrix. Find out its determinant. So let's find out B1. Sorry, this is the first term. Minus B2. Please tell me whenever I'm wrong. So all of these can be written as, we can see that B1, B2, B3 comes common in each and every one of these. Yeah. So then what do we have? A2, A3 into A3 minus A2 minus A1, A3 into A3 minus A1 plus A1, A2 into A2 minus A1. Right. So from this expression, we know that the rank of the controllability matrix goes less than n whenever determinant of the matrix is 0, right? So if we try to find out the conditions under which this expression goes to 0, then we'll be able to know when we'll have that the system is controllable or when it is not. So under what condition is the system, like, is this determinant 0?
Sir,
Yes.
B1 B1 B2 B3 जीरो हो जाए तब हो जाएगा, या
right?
सर A3 A2 इक्वल हो जाए, या A3 A1 इक्वल हो जाए, या A2 A1 इक्वल हो जाए।
Huh. So all three of them, if they are equal, then only, like, this is the condition, right? For
यस सर,
this expression being set.
डिटरमिनेंट जीरो।
Yeah. So, so the negative of this condition is bi not equal to 0. See, here you had bi equal to 0 for all I, right? So even if there exists like one bi, like sorry. So for all I, you now want that this condition hold, first thing. Then you want that ai is not equal to aj for all I and j, which essentially is the first condition. So under that condition, the system will be controllable. Now, yeah, so what this condition fails at is if bi not equal to 0, that is one necessary condition, obviously. But then also, if a1, a2, a3 all are same, then we could have that this determinant goes to 0. And now in this case, if b3 were 0, then obviously our determinant would also go to 0. So only this one option satisfies the conditions for the system to be controllable. So is it clear?
यस सर।
Yeah. So we'll move on to the next question. Yeah, okay. So before we go there, I'd like to show some MATLAB example. Yeah, just a minute. Yeah, my screen is visible, right?
या
So let's clear everything. Yeah. So in MATLAB, there is this very powerful thing known as symbolic toolbox. So what you can do here is you can initiate variables like we do in our pen and paper. You can initiate variables here, like here I do a1, a2, a3, b1, b2, b3. Then I can use these variables as regular variables like we do it in algebra and do some more computations using this. Okay, so I initiate these variables a1, a2, a3, b1, b2, b3. Then I declare the matrix A and B as it is in our question. So A is a diagonal matrix with a1, a2, a3 in the diagonals, and B is a column vector with b1, b2, b3. Then I find the controllability matrix, which is given by this B, AB, A square B. Right. Let's see what's happening. Let's first do this. So then you have A and B. So now we have A and B as in our question. Then let's find the controllability matrix. So this is the controllability matrix, right? So this is what we did in while solving the question as well. But you see how doing this in MATLAB eases your computational burden so much. Because if we had, let's say, a 4 cross 4 matrix, it would have been like quite difficult to get the closed form solutions like this. But MATLAB does it quite nicely. Then further you can find the determinant of C as well. Determinant of any matrix. So and this simplify function, what it does is it kind of brings a big expression into its simple forms. So let's see what we get. Yeah. So you see here, okay, maybe we did something wrong. 1 minute. So did we do any mistake while finding the determinant? Yeah, okay. Let's try to do that here because obviously MATLAB can be wrong. My screen is visible, right?
यस सर।
Yeah. Yes, sir. So maybe you guys can also try once again. Let's try to find out some mistake that we did. 1 minute. Yeah. So let's get a plain page. Here we have. So this is what we got for the control level of matrix, right? No issues with this.
Yes, sir.
So now let us try to find out the determinant. Yeah, so let's try that for 2 minutes, then we'll do it here. Yeah, so what do we get here? Am I missing something? Okay, I don't think there is a mistake here. Fine, I'll check out the solution and maybe the MATLAB functions as well and upload the correct solution. You guys can also try with this. But the process is clear, right? We just find out the controllability matrix and
Sir,
yeah,
you are right, sir. MATLAB, I think you get wrong answer.
uh, that is also most likely not correct, but maybe I have made some mistake in some code. I'll just check once. Right. So if the solution procedure is clear, maybe we'll move on to the next question. Yeah. So, okay. So the next problem that we have is we are given a system. This is the A matrix. This is the B matrix. And I think we have seen this A and B matrix quite a few times since the last week. And we want to find out the uncontrollable eigenvalues of this system. Right? So can someone tell me what an uncontrollable eigenvalue is?
Sir,
Yeah.
make matrix have an uncontrollable matrix, then find out the eigenvalue. Like when 3 cross 3 matrix, we make matrix of 3 into 3 like B, AB, A square B, then find the value of eigenvalue.
Yeah. Okay. So if I do that, I find controllability matrix B, AB, A square B. So this will always have a few number of eigenvalues, right? Like let's say this is a full rank matrix. That is, it has a rank of 3 in this case. Then how many eigenvalues do I get for this?
So 3.
I get 3 eigenvalues. So what does that mean? Does it mean that these eigenvalues are controllable or uncontrollable?
No idea, sir.
Yeah. So I'll just explain once what do we mean by this controllable eigenvalues and so on. So are you familiar with the controllable decomposition for an LTI system? So what we do is, if you remember what we did last class, we find out the controllability matrix first, then find out all the minimum number of the maximum number of linearly independent vectors from this matrix, column vectors from this matrix. So essentially, we take the image of this matrix, find its basis, that gives us a U matrix, alright, which will be n cross some n dash in size. So let's say C is full rank is 3, then this will be n dash. So since C is full rank, it will need 3 vectors in its basis. So U will be 3 cross 3, right? But let's say if C is rank 2, then this will be n dash. So we'll have 2 vectors in the basis of the image of C, and this U will be 3 cross 2. Then our transformation matrix will be U and some V, where V is just that the total matrix is linearly independent. The columns of the total matrix is linearly independent. Is it clear what I just said? Okay, maybe we'll just see with the example that will help us. Okay, so here let us find out C first. Please find out and tell me. Okay, so anyone found it? The first
So
column is B 0 1 0. Then what is AB?
so 101.
1 0 1. What is A square B?
So one so 111.
1 1. Okay. So what is its rank?
So 2.
Rank is 2. Correct. So can you tell me which are the independent columns?
No idea, sir.
Anyone else? Okay, so remember what we did last time. So this is C. Then the image of C is A 0 1 0 plus B 1 0 1 plus C 1 1 1 for all values of A, B, C real, right? So basically the image of C, this matrix C, is the is all possible vectors which can be generated by these three column vectors, right? Like this, by a linear combination of these three column vectors. So how can I represent any vector of this form as, so what rank 2 means is, so you know that a rank of a matrix can be its row rank or column rank, both have to be same. So what rank means is, let's take column rank. It means that there are only two linearly independent columns and the third one must be dependent on the other two. Okay. So, and similarly, in case of row as well, there are only two linearly independent rows and the third one has to be dependent on the other two. Right. So tell me what is the what are the linearly independent columns in this matrix? So how do we find out what is a like whether two vectors are linearly independent or not? Okay, let's just take some time on this. So let us say we have a vector A, B, C, or let's say alpha 1, beta, alpha 2, alpha 3, and a vector beta 1, beta 2, beta 3. Okay, these two vectors are said to be linearly independent if, okay, let's take linearly dependent first. These two vectors are said to be linearly dependent if there exists non-zero A and B such that is equal to 0 for some A comma B not equal to 0. So if you can find some non-zero real values whose and using them as coefficients for these two vectors, if you can find an expression which goes to 0, then these two vectors are linearly dependent. And if they are not linearly dependent, then they are told to be linearly independent. So if we have, let's say this is x1, x2. If I have, let's say x1 till xn, then these n vectors are linearly dependent if there exists non-zero coefficients ai such that this expression goes to 0 for some, like it need not happen for all ai, but there if there exists some ai which is not equal to 0 and this expression goes to 0, then we have that this these vectors are linearly dependent. Is the definition clear?
Yes, sir.
Okay, then let's take some basic examples. Let's take the this case itself. 0 1 0. What was it? One. So let's take this example. Tell me whether this control this matrix, these, let's say this is x1, x2, x3. Tell me whether these are linearly dependent or not.
So may be dependent.
Linearly dependent? How can we say so? Tell me three these coefficients that make them linearly dependent.
So A1 is 1 and A2 is 1 and A3 is minus 1.
Right. So you can, in these three things, you can clearly see that x1 plus x2 results in x3. Right. So that means that these three vectors are linearly dependent. So from this controllability matrix, its image is the span of these three vectors, span of x1, x2, x3. So what is the span of some vectors? It's basically the set of all alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3 such that alpha 1, alpha 2, alpha 3 are real numbers. The set of all possible vectors which can be written in this fashion, basically the span of these three vectors is basically all possible linear combinations of those three vectors. So this is a linear combination. So now what do we want to know? We want to find out the image of C, right? So if I have, so from this, what do we know? This implies x3 can be written as minus a1 x1 minus a2 x2 by a3 because a3 is not zero. So that means I can write Yes, you're saying something? Any questions?
No, sir.
Okay. Yeah. So alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3. If I substitute x3 as this into this, then what do I get? Alpha 1 x1 plus alpha 2 x2 plus alpha 3 minus alpha 3 by a3, a1 x1 plus a2 x2. That is alpha 1 minus alpha 3 a1 by a3 x1 plus alpha 2 minus alpha 3 a2 by a3 x2. So any linear combination of these three vectors, since these three vectors are linearly dependent, this linear combination can be written as a linear combination of only these two vectors x1 and x2. Is this part clear?
Yes, sir.
Okay. So then, so what do we have now? Yeah. So now tell me, what is the image of C? How can I write it as a span of two vectors? Which two vectors should I choose? It is evident here, right? So any vector of this general form can be written as a linear combination of these two vectors. So I can essentially write this as span of x1 and x2. So this will form my U matrix in this, right? The U matrix. Is this part clear? This is very important. Is it clear?
Yes.
Yeah. So we have U. Then our transformation matrix T will be U, which is 3 cross 2. Then we want another 3 cross 1 vector here so that we get a non-singular matrix T. So we want a V here. So V has to be such that T is invertible. Now T is invertible if it is full rank. So what is the rank of U? Rank of this matrix?
Sir,
Yes. Yeah.
2.
Rank is 2. Why?
Sir, when row, row 2 shift to at R1, then R, then R2 R2 minus R3, then R3 row becomes 0.
No, no, I don't get it. What?
सर रो 2 को रो 1 से रिप्लेस कर दीजिए.
Okay. रो 2 को रो 1 से, okay. Then,
सर रो 3 लिख दीजिए 0 1. सर R3 माइनस R2 कर दीजिए.
right. So this gives us, yeah. So
सर अब
in this process of row transformations, what you're essentially doing is you're trying to see if there is a row which is linearly dependent on other rows, excluding itself. Right. So this third row 0 1 is dependent on row 1 because it is equal to it. So these two row vectors 0 1 0 1 are linearly dependent. Right. So if you wanted to find out some coefficients, let's say this is y1 y2, then a1 y1 plus a2 y2 equal to 0. Clearly a1 equal to 1 and a2 equal to minus 1 satisfies this expression. So rank essentially means the number of independent rows or the number of independent columns. So you need to ingrain this idea because it is quite crucial in the linear algebraic framework that we study LTI systems with. Now tell me whether these two vectors are linearly dependent or not.
So not dependent.
Not dependent, right? So that is why, since this matrix U has two linearly independent columns, that is why its rank will be 2, right? If it had one column, like two columns, one of which is dependent on the other, then its rank would have been 1. So that is the basic definition of rank. This determinant equal to 0 is something that comes out of some derivation from this definition. It is not a like this. The number of independent columns or the number of independent rows is a more basic definition for the rank of a matrix. All right. So T is our transformation matrix. I want T to be invertible. So that means rank of T has to be equal to 3. So we know that rank of U is 2. That means two independent column vectors, columns. Now I want V such that total T has 3 independent columns. Right? Is it clear? Whatever we have done till now?
Yes, sir.
Okay. So, it is just okay. So I now have T is equal to T is equal to 0 1 0. What was that? 0 1 0 1 0 1. Now tell me a vector which is linearly independent of these two.
So maybe 110.
1 1 0. So, okay, let us just verify once whether we can we write 1 1 0 as a linear combination of these two? So, if we could do that, then this would be B, A, B. But then B equal to 1 and B equal to 0, which is not possible, right? So, 1 1 0 is a linearly independent vector. So, we can create the T matrix like this. So, now I'll transfer to a new variable z from x. So x equal to tz. So how will our differential equations transform? We have x dot equal to ax plus bu and y equal to cx. So z dot will be what? T inverse x dot, that is T inverse ax plus T inverse bu, which is T inverse a tz plus T inverse bu. So z dot is this and y will be, so note that input and output won't change. States are just fictitious variables which we are creating to understand the system, but inputs and outputs are quite physical in nature, so they won't change. So y is equal to cx, that is ctz. So now if I write this as something like this, then I have a tilde is t inverse at, b tilde is T inverse B, C tilde is CT. Okay, so this is our transform system, LTI system. Now, what controllable decomposition says is, if we took a T like what we have taken, that U and V, where U forms the basis for the controllability matrix image, and V is just to make the matrix non-singular, then this A tilde will be of this form: AC A12 0 AU, and B tilde will be BC 0, right? So let us find it out. For the given T that we have taken, 0 1 0 1 0 1 1 1 0, find out A tilde. Let's take some 5 minutes to try this out, then we'll look at its solution.
Sir,
Yeah,
sir, please show a matrix.
A matrix set, I'll just write it down here. A is 1 1 0 0 0 1 and 0 1. This is the A matrix, and B matrix is 0 1 0. Okay, find it out. Okay, first tell me what T inverse is. You can use a calculator as well.
Sir, 2 minutes.
Yeah.
Done, sir.
Can tell me? Yes, T inverse anyone?
Sir, T inverse.
Yeah,
So -1,
-1.
-1, 0, bottom. 1,
Hmm.
1,
Hmm.
0, 0.
Okay,
1, 1, -1.
correct. So this is the T inverse matrix. Now what is A tilde?
Sir, 0,
Hmm.
0, 1, 0.
A bottom or
Sir, bottom.
0,
Bottom,
1,
bottom.
0?
1, 1, 0.
Hmm.
-1, 1, 1.
Okay.
Yes, sir.
So what did we tell? That the the A tilde matrix will be made like decomposed into these matrix blocks, where this one will correspond to the controllable part and this one will correspond to the uncontrollable part. So what is the rank of our C matrix? The rank of our C matrix is 2. Okay. So that is why we'll have a controllable portion of order 2 and an uncontrollable part of the remaining order from 3, which is 1. Okay, so here you can see this is the AC matrix, this is the 0 block, this will be the AU matrix, this will be the A12 thing. Okay, so the eigenvalues corresponding to AC will give me the controllable eigenvalues, and eigenvalues corresponding to AU will give me the uncontrollable one. So basically, if the uncontrollable eigenvalues are strictly negative, then the system is called stabilizable. Why? Because the controllable eigenvalues we can control, so we can place them anywhere we like. But the uncontrollable one we can't. So if that is strictly negative, then the system corresponding to that eigenvalue will at least go to 0 on its own, even if we can't control it. So that is the like idea behind stabilizability. Okay, so in this, what is the eigenvalue of this AU?
So 1.
1, correct. So 1 is the uncontrollable eigenvalue. And let's just verify these things on MATLAB. Yeah, able to see my screen?
Yes, sir.
So I have declared all A, B, C, like found the controllability matrix, and taken this transformation matrix which we considered. So there you see these are the controllable eigenvectors corresponding to the controllable eigenvalues. So this matrix has two controllable eigenvalues given by -0.618 and 1.618, and one uncontrollable eigenvalue given by 1. Okay, is it clear?
Yes, sir.
Yeah. So I'll share my writing part once again. So this system is not stabilizable. It is purely uncontrollable. So if you look at this, which are the uncontrollable eigenvalues of the system. So this is the correct answer. Lambda equal to 1 is the only uncontrollable eigenvalue. The rest, these two, they are controllable. Alright, is it clear? Should we move forward?
सर
Yeah.
अगर सर आइगन वैल्यू जो हमारा 1 था, अगर -1 आया होता तो हमारा स्टेबलाइजेबल होता।
System stabilizable होता है. Yes.
अगर सर प्लस आता है तो नहीं होगा, माइनस आएगा आइगन वैल्यू अनकंट्रोलेबल का तो हमेशा स्टेबलाइजेबल होगा।
If the uncontrollable part eigenvalue is has a negative real part, then the system will be stabilizable.
ओके सर।
Okay. So next we move on to another problem. So we are given an LTI system which is a homogeneous system. There is no control. So we want to find out using MATLAB's Lyapunov function the solution to the Lyapunov equation given by this, and then its resulting Frobenius norm. So I'll move over to MATLAB for this. So look at this. First, let us declare the matrix A. So this is the matrix we had, right? Then we have another function named Lyap. I'll see. Lyap solves continuous time Lyapunov equations. So if you put x equal to Lyap of AQ, then what it will solve is this: AX plus X A transpose plus Q equal to 0. So what is the equation that we want to solve? We want to solve AM plus MA transpose is equal to minus I. So you can see that this is in that form. So we want to find this M, which here is X, and Q for us is I. So that I can do by this M equal to Lyap of A comma. So this takes only two inputs. One is the A matrix A and another is the Q matrix, which for us is the identity matrix. Okay, so M matrix is given by this. Then further to find its Frobenius norm, all we have to do is put in the norm function and we get this. Is it clear?
यस सर। सर
Yeah.
सर व्हाई यू फ्लो इन नॉन फ्लो फंक्शन व्हाई?
Because we wanted the Frobenius norm. If you use normal this norm of M, it gives us the 2 norm, not the Frobenius norm.
ओके सर।
Okay, clear?
यस सर।
हाँ, tell me.
सर एग्जाम में मैटलैब अलाउ नहीं होगा तो कैसे करेंगे, क्योंकि एग्जाम में तो मैटलैब अलाउ नहीं होगा।
The exam में mostly they won't ask questions of this kind like wait 1 minute.
लाइक प्रीवियस वन सर।
Like which previous one? Question 2 or
यस
question
सर।
3 only? Question 2 we solved here, no? We found out T inverse AT. Then we found
यस
out
सर।
which is the uncontrollable eigenvalue.
यस सर।
Yeah. So then this one, if like this, you can also solve. You just have to take M equal to some, assume something like this: M1, M2, M3, M4, M5, M6, rest are 0. Sorry, rest are symmetric. So M2, M3, M5. So then you can just, you'll get 9 equations and these 6 variables must satisfy them. Then you'll get a set of equations which you can then solve to find out. Just that since it's a 3 cross 3 case, the things will be very like messy. So if it's a 2 cross 2 case, you can perfectly solve it using normal pen and paper. So for this, the solution is this. Okay, is it clear?
यस सर।
Okay. we move on to the next question. Again, we have an LTI system with an A and B matrix given. Which of these following statements are correct? So let us start one by one. Is the matrix A Hurwitz? So what a Hurwitz matrix is all the real part of all eigenvalues is strictly negative. So let us first find out the eigenvalues of this A matrix. Let's do that for some 3-4 minutes, then we'll discuss. Yes, do you have any eigenvalues?
So 1, -1, -5.
Okay. So so then what? Is this matrix Hurwitz?
No, sir.
Why? Because for a Hurwitz matrix
All
we need
eigenvalue, sir, all eigenvalue is not less than 0.
right. Now, okay. So next, what do we need to find out? So this is not true. Next, what do we need to find out? Is the pair of matrix A and B controllable? So find out the controllability matrix. So tell me what is the controllability matrix?
Sir, second column 1, 0, 1.
101, okay. Third column.
एक
Yeah. A trick to finding a square b faster instead of computing a square is just to multiply a with ab. Because you have already found ab, just multiply a in front of it. So, and this is a, ab is nothing but b, right? So a square b is nothing but a into ab, which is a into b, which is again just b. Correct?
Yes, sir, correct.
So now tell me what is the rank of this matrix?
Sir, 1.
Okay, why is it?
Sir, root 3. Sir, root 3 minus R1,
Yeah,
0, R3, root 3.
okay. Yeah. So yeah, also remember that you can do the similar computations along columns as well. Like you are doing R3 equal to R3 minus R1. You can also do C2
Yes, sir.
equal to, yeah, those things. So then rank is 1. So then obviously the system is not controllable. Now is it
Yes, sir.
stabilizable? Sorry. Hmm. So is it stabilizable?
Yes, sir.
How can we say so?
Sir, eigenvalue -1, -5.
For
सम
what?
पार्ट स्टेबलाइजर, सर स्टेबलाइजर वही होता है जो कंट्रोलेबल, सब अनकंट्रोलेबल, मतलब कंट्रोल पूरा अनकंट्रोलेबल ना हो, कुछ पार्ट उसके कंट्रोलेबल हो।
हाँ, but इसमें कौन सा, but how do we know which eigenvalues are controllable and which are not?
आई थिंक सर -1, -5 गेस।
No, but how do you guess that? The thing is, you have to do the controllable decomposition, right? What we did in the previous to previous problem.
यस सर।
Here we found out this A tilde, no? Which is T inverse AT. Then you found out whatever the controllable part is and what the uncontrollable part is. So we have to do the same here as well. So T is equal to UV. We know that. What is U? So what is U?
सर,
Yes.
सर कोई और मेथड नहीं है स्टेबलाइजेबल निकालने का, क्योंकि सर बहुत ये लंबा मेथड हो जा रहा है।
The method is long, but that is the only way because you have to find out which eigenvalues are uncontrollable, and then only you can say something. There are other methods as well. We'll come to it just a little later.
Okay, sir.
So let's just do this one more time. So what is the U matrix?
Forget, sir.
Okay, so U is essentially the image of the C matrix, right? So give me the rank is 1. So how many independent columns does this matrix have?
So 1.
1. So what is the independent column? We can take any one, right? 1, 0, 1.
Yes, sir.
So U is this because here rank is 1. So U will also be only 3 cross 1. So this is 1, 1, 0, 1. Then we have to take two other columns which will make V such that T is invertible. So we can take a any two linearly independent columns so that the T matrix is invertible. So one possibility is this and this. Is this a invertible matrix?
Yes, sir.
So then, okay, since this method is getting long, we can just do the rest of the part in MATLAB. Okay, so the procedure is same. Let's just check out what the solutions are. Okay, you have this A and B matrices, which gives us this controllability matrix, right? This was what we obtained. Then, yeah, so I am taking this T matrix. So T is, this is what we have taken, as we showed in the writing part. Then the new transformed A matrix will be T inverse into A into T. So what is that? It is this. So remember that you will get an first a controllable block on the top left of size equal to the rank of C. So rank of C is 1. So here this corresponds to the controllable part. So the controllable eigenvalue is 1, while this square block -1, 0, 0, -5, that corresponds to the uncontrollable part, right? So controllable eigenvalue is 1 and uncontrollable eigenvalues are -1 and -5. Since the uncontrollable eigenvalues are stable, the system is stabilizable. Is it clear?
Yes, sir.
Okay, no issues with this. So that means the particular matrix we have considered, the system that we have considered, that has a that is a stabilizable system. Yeah. So this is the solution. Okay. Then we move forward to the question previously asked. Are there any other ways of? Yes.
So previous one question.
Which question?
So 4. Sir, can we always say when matrix is not controllable, then it's stabilizable?
No, no. That you can't say. You can easily find examples where the like essentially the matrix has to have a positive eigenvalue which is uncontrollable, right? let us try to cook up an example that should be possible. Okay, so let's take this system. Okay, I think okay, let's take C matrix. It is 0 1. Okay, this system is controllable, right? Let us edit it to get a uncontrollable system. Yeah. Let's say this is the case. Then this system is not controllable, correct?
Yes, sir.
So now tell me what are the eigenvalues of A? So the eigenvalues will be given by determinant of this equal to 0. So this implies lambda is equal to 1 comma 1, correct?
Yes, sir.
So what does that mean? The system is not controllable, that is clear. So rank is what? 1. Now if you decompose the system into controllable and uncontrollable parts, no matter what you do, since both of the eigenvalues are positive and only one can be controllable because the rank is 1, so this system is not stabilizable. Is it clear?
Yes, sir.
Yeah. So it is not
Sir,
always
not stabilizable.
yeah, the system will not be stabilizable, right? Because you have rank of C matrix as 1. So there will be only one controllable eigenvalue from this second order system and one uncontrollable eigenvalue. But since both of the eigenvalues are positive only, like they have a positive real part, so either ways only one will be uh, controllable and the other has to be uncontrollable. And since one of the uncontrollable eigenvalues has a not like a positive real part, so the system is not stabilizable. Is it clear?
Yes, sir.
Yeah. Now let's move on to the next question. If a continuous LTI system is stabilizable, the following statements is or are correct. Now, these actually happen to be equivalent tests for stabilizability. Okay, so if so, like we found out, like earlier we had to do this controllable decomposition and so on, and then find what the uncontrollable eigenvalues are. There are some easier ways to do to find whether a system is stabilizable or not. Okay, so if there exists a positive definite matrix P such that this inequality is satisfied, then the system will be stabilizable. Also, if there exists a positive definite matrix P such that this inequality is satisfied, then also the system is stabilizable. And finally, if the rank of this matrix for any positive real lambda then is n, then also the system is stabilizable. So let's try that with the previous question. We had this A. 1 minute, I'll write it down. 0 3 by 2 minus 1 2 3 1 2. So what were the eigenvalues of this? 1, minus 1 and minus 5, right? Lambda equal to 1, minus 1, minus 5. So let's try this particular case. So by the way, all these three are equivalent tests for stabilizability. Okay. So let's try this third test for all eigenvalues with positive real part. Rank of this is n. So let's take this because there is a positive real part. So we have to prove that rank of a minus lambda I, lambda is 1, so a minus I comma b is n. N is what? 3 here. Okay, so let us do that. Find out what this matrix is first. A minus lambda I and B. What is this? I remember that B was 101.
Sir,
Yeah.
sir here यानी ये order of A matrix.
Order of
A matrix.
let
Sir, option number 3 यानी present the order of
yes,
matrix A.
A matrix, yes.
Okay, sir.
Okay, so we can try this and then you can verify that these are similar tests. I'll write down one more test for stabilizability, which essentially says that every eigenvector of A transpose corresponding to an eigenvalue with positive or zero real part is not in the kernel of B, in the kernel of B transpose. Okay, this is another equivalent test. Just give me a minute.
सर
Yeah.
रैंक सर 3 आ रही है, सही है.
हाँ, तो so the stabilizability thing holds. Yeah, just a minute. I'm just checking for other tests, or else I'll update all the tests. I think these cover all of it. I'll update this with the slides that I upload. Yeah. So okay. Then next we move on to this question. Okay. What was that? Yeah. So now consider the system given here. A is given some 2 cross 2 matrix, B is given some 2 cross 1 vector. Which of the following are correct? Okay, this is a simple thing. Like first, let us find out the rank of A, B. What is it? Basically the rank of 2 minus 1 minus 2 1 1 1. What is the rank of this?
Sir, 1.
1. Why is it?
Oh.
Yeah, why is it 1?
Sir, 2. I think 2.
Yeah, why do you think it is 2?
Sir, because both two rows are linearly independent.
Right. So, or else you can also see that these two columns are linearly dependent, but these two columns, they are linearly independent. Okay, so the rank is 2 for this. So these two are wrong. Then we have to find out that lambda equal to, like, what is an eigenvalue for a plus bk. This is capital B. Okay, what is the for any 1 cross 2 matrix K? Okay, let's just so we have A given by this, and B is 1. So I want to find out the eigenvalue of A plus BK, where K is any 1 cross 2 matrix, any general matrix 1 cross 2. So what is A plus BK? This is A plus B into K is K1, K2, K1. That means this is 2 plus K1 minus 2 plus K2 minus 1 plus K1, 1 plus K2. So find out its eigenvalues. Let's take some 5 minutes for that. So any updates? So what are the eigenvalues? Determinant of this we have to find out equal to 0, right? So what is the determinant? It is lambda minus 2 minus. So this gives me a quadratic equation, right? In lambda minus 3 plus k1 plus k2 lambda plus 3 k1 plus k2. So for now, assuming this is true, let's find out the solutions of this quadratic. Tell me what should the solution be? Standard b square, that a x square plus bx plus c formula. Yes?
So minus b plus minus under root b square minus 4 is c upon 2a.
Yeah, okay. So for this, we can directly put it 3 plus square of this. So let's write k1 square plus k2 square plus 2k1 k2 plus 6k1 plus 6k2 plus 9 minus 12k1 minus 12k2 by 2. So does this simplify? So you can verify that this, since you just change minus like plus 6k1 plus 6k2 minus 12, so it will become minus 6k1 minus 6k2. So this can be written as k1 plus k2 minus 3. Okay, so by 2. So this means there are two possible eigenvalues. One is 3, the other is k1 plus k2. So this first eigenvalue does not depend on k1 and k2. And that is what we wanted to find out. Rank we found out as equal to 2 of A and B. Now we see that lambda equal to 3 is an eigenvalue of A plus BK for any general 1 cross 2 matrix K. Right. So, so that is how we find this. Well, obviously for an exam point of view, you can just pick any general, like any particular K, let's say 1, 1 or something like that, and find out the eigenvalue of this A plus BK matrix. Correct. So then, okay, let's keep this for a little later. Okay. Now we have a continuous time LTI system is given by, we have some values A, B, and a transformation matrix of the form T equal to something. Okay. So if you remember, the transformation matrix must have U and V, where U is the basis for the image of the controllability matrix. Correct. So in this, what is the controllability matrix? It is 1 minus 1. Then AB will give you 0, 0. So what is the rank of this?
1.
So 1.
1. So the independent column that we have is 1 minus 1. Right. So you can take U as 1 minus 1, which here we have. Then we have to take some V such that this T is non-singular, right? So one trivial case is what? We can take
So 0, 1.
0, 1, right? So if you take 0, 1, just give me a moment. Yeah, if you take 0, 1, then t is equal to 1 minus 1, 0, 1. What is its inverse?
Sir,
Yeah,
so 1,
1,
0,
0.
bottom,
Okay,
bottom. नहीं सर सही सर 1 bottom 1
okay,
0 1.
correct. So
Yes
you
sir.
can verify that this is the inverse of this given T matrix. Now what is T inverse AT?
Sir
Yeah,
0
0.
bottom 0
Okay.
1 4.
Yeah, so this is the correct A transformed A matrix. So what is the question? The portion of state matrix corresponding to the uncontrollable state AU. So what is it? So we know
4.
by doing this, yeah, decomposition we get AC, and it obviously depends on the rank of the controllability matrix, what size and all will have. So this will be AC, this will be AU. So AU equal to 4. But now comes the important question. Let's say instead of this particular V, I used some other V, right? Will then I have this AU equal to 4?
Not necessary, sir.
Okay, why do you say that?
So because we can take 1 and 0,
Hmm.
then we can find T and T inverse.
Okay,
It may be
let's try that. Let's take 1 minus 1 and 1 0. Let's try the same process. I know it's getting a little tiresome, but let's just try this. Then we'll see something. So what's T inverse?
so 1 1 1 1 0.
No sir.
I don't think.
-1 the right hand side upper.
Right. Yeah.
Yes sir.
No, I don't think this is also. No, this does not form the inverse, right? It's just what do we? So determinant is 1. So here I have 1 0. Is this the inverse? T inverse into T. What is it? 1 into 1. I get 2, right? Yeah. Uh, so I don't know. Let's just use a calculator. Give me a minute. Oh, okay. We forgot this. This portions will be interchanged, right?
Yes
Yes.
sir.
So this is the inverse, correct? Then what is T inverse AT? Let's find out quickly. T inverse A is minus 3, minus 3, 4, 4, then 1 minus 1, this 0, then this is minus 3, 0 is 4. So what did
Yes,
we
sir.
get here? AU is still equal to 4. So even if we change this V, we still got the same AU. Why do you think that is happening?
सर मल्टीप्लाई करने से सब कैंसिल हो जा रहे हैं शायद।
No,
सर
the
टी इनवर्स 80 मल्टीप्लाई करने से सब पहले जैसे मैट्रिक्स बन जा रहे हैं शायद।
no, the thing is because since this order of the uncontrollable part is 1, it has to be equal to the eigenvalue. And uncontrollable eigenvalue will remain same no matter what transformation you use. Since eigenvalues are preserved under different transformations, so that is why the controllable eigenvalue, which is 0 here, and uncontrollable eigenvalue, which is 4 here, those will remain same. And this you can see this A12 portion that changed, it became -3 instead of 1, but the eigenvalues will remain same. If you had a bigger matrix, then obviously the AU and AC portion could have changed, but the eigenvalues they would have remained same. Since this is a like order of controllable and uncontrollable parts are one only, you will directly get the eigenvalues at the diagonal thing. So this 4 will remain same no matter what transformation you use. Is it clear?
यस सर।
Yeah. So for this, the previous question, it is a straightforward one. I have uploaded the MATLAB code for it as well. So you just have to discretize the system like we discussed in one of the previous sessions, and then just use standard controllability matrix and stuff. Okay. So with that, maybe we'll end for today. Are there any doubts?
सर
Yeah.
हमें एक क्वेश्चन पूछना है।
Please go ahead.
ये सर
Yes.
सर आपने रीचेबिलिटी के लिए बताया था कि सर हमें किसी ओरिजिन से किसी एक पॉइंट पे हम सर जाते हैं।
हाँ.
सर उसमें जो सर हमारा सब स्पेस होता है, सो इमेज होता है कि नल स्पेस होता है?
मतलब I don't get the question.
सर जैसे सर किसी पॉइंट से हमको रीचेबिलिटी के लिए किसी पॉइंट से किसी पॉइंट पे जाते हैं। सर जैसे 0 से टी नॉट पे 0 पे गए, 0
Correct.
पॉइंट है और T1 पुट करने पे किसी स्टेट पे गए X1 हम
State
पाते हैं।
correct.
तो सर जो X1 होता है,
हाँ.
सर जो ये क्या कंटेन करता है? सर किसी एक इमेज को कंटेन करता है या नल स्पेस को कंटेन करता है?
It is the image of the controllability matrix. So
सर रीचेबिलिटी
reachability,
कंट्रोवर्टी का इमेज कंटेन करता है सर।
like for LTI systems, both reachable and
यस
controllable
सर।
subspaces, they are the image of the controllability matrix. Okay. But in general, for more general systems, the reachable subspace is the image of the reachability Gramian, and the controllable subspace is the image of the controllability Gramian.
सर वंस अगेन सर।
Yeah, I'll just write it down in a minute. So the reachable subspace is the image of the reachability Gramian, and the controllable subspace is the image of the controllability Gramian. Okay.
ओके सर।
Yeah. Is it clear?
यस सर, थैंक यू सर।
Yeah. Okay. So with that, we'll end for today. Thank you for attending the session.
Thank you, sir.